Hi there, welcome to my new video. Today I want to show you a small electronic measurement unit housed inside this casing. The idea for this device came during a brainstorming session with a friend who had previously used a Proton magnetometer that I built. They took it to a mysterious place in France called Bugarach, a location some people believe even aliens like. So let's take a virtual trip there and continue the story on site. This is one version of the Proton magnetometer designed to be carried in a backpack. The sensor is mounted at the bottom on a spacer to keep it away from the electronics and battery. This version still has a display, but the latest one doesn't have any. It connects to an Android app through Bluetooth. The smartphone's internal GPS and storage capabilities make the design much simpler and more efficient. Here's a picture of my friend using the magnetometer in Bugarach. And here are the results of a typical magnetometer survey. A color scale range of ±100 nanotesla is usually sufficient in areas without magnetic anomalies. Along the walking path, fluctuations were less than 20 nanotesla, with a few exceptions possibly caused by metallic objects on or beneath the ground. Such measurements are consistent, showing similar results on repeated surveys, sometimes with slight offsets due to slow natural magnetic field variations. This graph shows the GPS altitude and measurement accuracy during the survey shown earlier. The data looks smooth and stable, as expected for modern smartphones. We used the Samsung device. But let's return to the original site. The color scale is the same, but here we see extreme values, especially in this area. There's a road with electric lines nearby, but these typically don't cause such strong disturbances. 2 days later, measurements in the same area revealed far less fluctuation. Flipping back and forth makes it pretty obvious, although the paths were not exactly the same. However, static significant magnetic deviations persisted, suggesting metallic material in the underground. Here you can see the GPS data points recorded on the first day, sampled every second. The signal was so erratic that my friend thought his GPS was broken. The altitude unexpectedly dropped to 0, then gradually increased before suddenly returning to normal. This map shows the GPS accuracy during the first survey. Strangely, poor accuracy seems to correlate with the locations of erratic magnetic values. Since both the GPS and magnetic data are discrete samples, it's possible that the disturbances were highly variable, affecting each system at slightly different times. This picture shows 2 Proton magnetometer sensors during construction. The main components are the coils used to both induce and sense proton precession, which occurs at frequencies between 1 to 4 kHz in the magnetic field of the Earth. Disturbances in this low frequency range can affect the measurements. But where could these disturbances come from? And what even disrupted the GPS during the first survey? There's no visible evidence of machinery or underground installations. Unfortunately, we can't just climb down to find out. As a next step, we decided to hide the unit showed at the beginning. It's a data logger. Let's take a closer look inside. On the left is an induction coil connected to a 3-stage amplifier, using a low-power op-amp running at 3.3 volts. The amplifier's output feeds into the microcontroller on the right, which also manages the data storage on the SD card in the center. This graph shows the current consumption over a 12-second cycle. Every 2 seconds, the system takes 8,192 samples at 9.6 kHz sampling rate and then stores the data. Between sampling periods, the system sleeps, consuming just under 5 milliamps, not perfect, but sufficient for a few days of recording. During sampling, the current raises to around 14 milliamps, with the SD card consuming the most power during data storage. Over 12 seconds, the charge drawn from the battery is less than 0.05 mAh, meaning a good quality battery should keep the system running for 3 days or more. I was shocked by the number of fake batteries on the market. I bought one claiming a capacity of 4,200 mAh, but it turned out to have less than 900 during my test. Once the logging period is over, software like the Free Spectrum Lab can analyze the sample data blocks. Using an FFT of the same size like the blocks works well. Listening to the data over a speaker reveals clicks at block boundaries, a drawback that can't be really avoided, since measuring while writing to the SD card is not possible because of the severe disturbances due to high current fluctuations picked up by the induction coil. So I'm hoping my friend will return to Bugarach this year to hide the logger for a few days, so that we can discover when these strange underground machines, or whatever it is, are active and what frequencies they emit. As a scientist, I don't really expect anything unexplainable, but it's an exciting little project, and who knows, right?